in this last video of the section, we have no new concepts to learn. So this is definitely good news. We know everything that we need to know in order to solve limits of this form. Now let's look at the limit. The limit is still at infinity. That hasn't changed. What I noticed, however, changed from the previous video is that this function is not a rational function, and that's because of the square root in the denominator. Even though I have a polynomial on top, I have a polynomial inside of the radical. Because of the radical, this function here is not rational. That means that if I want to find this limit right here, I cannot use the shortcut that we developed for rational functions. So that's kind of a bad thing. The good thing, however, is that since I cannot use the shortcut, I will still be able to use a similar approach to what we did before developing the shortcut. Before we knew about the shortcut for rational functions, if you remember, we were taking the largest power of the denominator and we were dividing every single term by that power. I am going to follow something similar like that approach for non-rational functions. All right, so I want to show you how to tackle limits of non-rational functions like this. And I want you to notice that the process will be very similar every time that you encounter a radical within these functions. I'm going to go slowly so that you can really follow me here. And remember that you can always pause the video and re-watch any particular segment of this discussion. So every time that you have a non-rational expression and one where a radical is involved, what I want you to do is to go ahead and to look at the polynomial inside of the radical and to factor the largest term, the largest power. Here the largest power is x to the 7th. Let's factor that out. So if we do that, we're going to have the limit as x approaches positive infinity, 4x squared plus 9, that's not going to change right now, divided by the square root of x to the 7th, and then here we're going to have 1 plus 6x squared over x to the 7th minus 5 over x to the 7th. Close brackets and always extend the radical. So if you notice right here, what I did was I came and I factored x to the 7th, the largest power of the quadratic, and I readjusted all of the other terms over here because of that factorization. Then we are going to go ahead and we will leave the numerator as is for now. And we're going to use properties of radicals. So I want you to remember, I'm going to do it here on top in green, that if we have the square root of a times b, this is equal to the square root of a times the square root of b. In other words, I can take the square root of a product and I can split the square roots into each factor, as long as I keep the operation of multiplication between those two factors. This is a very known properties of radical. So I'm going to go ahead and apply that to x to the 7th as one factor and this sum over here as another factor. So then this is going to be equal to the square root of x to the 7th times the square root of 1 plus, and I will now simplify 6x squared over x to the 7th. That will be 6 divided by x to the 5th minus 5 over x to the 7th. Let's look at the limit here. As x goes to positive infinity, the square root of x to the 7th is beautifully defined. That means that if x is going to positive infinity, all of these x values over here are going to be positive. So x to the 7th will be positive. My square root is beautifully defined. What I am going to do now is to change this radical into exponent form, right? We know that every radical can be expressed in exponent form. So this will be equal to the limit as x approaches infinity of 4x squared plus 9 divided by x to the 7 over 2, and then the other radical will stay as is. 1 plus 6 over x to the 5th minus 5 over x to the 7th. What you will do now, once you get to this step right here, let's recap. We factored the largest power from the denominator. Then we separated the radicals once we had x to the 7th times this quantity. Then we noticed that at positive infinity, the square root of x to the 7th is always defined. So we came and we continued by changing the radical to exponent form. Now that we get to this step over here, what we will now do is we will divide the top and the bottom by x to the 7 over 2. And this is where this process is similar to the process of limits at infinity of rational functions before we knew the shortcut. We now take this factor over here, x to the 7th over 2, and we will divide every term on top and the entire denominator by x to the 7th over 2. So this is how this will look. This will be equal to the limit as x approaches infinity of 4x squared over x to the 7 over 2 plus 9 over x to the 7 over 2. All this divided by x to the 7 over 2 times this square root here, 1 plus 6 over x to the 5th minus 5 over x to the 7th, and this will also be divided by x to the 7 over 2. So now let's start simplifying. This x to the 7th over 2 will cancel with x to the 7th over 2. This over here can be simplified by properties of exponents. So I'm going to go ahead and continue that simplification process here on the right. So the limit as x approaches positive infinity, when we simplify the first term, we are going to end up getting 4x to the negative 3 over 2. Then over here, there's nothing to simplify. 9 over x to the 7 over 2. All this will be divided by the square root of 1 plus 6 over x to the 5th minus 5 over x to the 7th. Now, what I will do is the following. I will apply the limit to the numerator and the limit to the denominator. So then that's going to give us the limit as x approaches positive infinity. Another thing that I'm going to do is I'm going to take this negative exponent and turn it positive. So then that's going to give me 4 divided by x to the 3 over 2 plus 9 over x to the 7 over 2. And all that will be divided by the limit as x approaches positive infinity of this square root, 1 plus 6 over x to the 5th minus 5 over x to the 7th. Now, we are ready to evaluate the limit in the numerator. In the numerator, if I now apply the limit to the first term and to the second term, we are going to get 0, and 0. So I am going to have immediately 0 plus 0 in the numerator. In the denominator, I want you to remember that another limit law is that we can take the limit inside of the radical. So we have 1 plus 6 over x to the 5th minus 5 over x to the 7th. And now again, you can do something very similar. I will just skip this step because it's just taking too long. We will now apply the limit to the first term, to the second term, and to the third term. And when we do that, we're going to have 0 in the numerator over the square root of 1 plus 0 minus 0. So then that's going to be equal to 0 over the square root of 1. That is going to be equal to 0. So then, beautifully, we found that the value of this limit at positive infinity is equal to 0. Here we have another limit of a non-rational function, and this is very similar, if you notice, to part A. I wanted us to practice those same steps once again. The only tweak here is that now I gave you a limit in both directions, at positive and at negative infinity. In part A, the limit was only in one direction, positive infinity. Here we have two directions, and I want to show you how to handle that in case these problems appear in the homework assignment. So let's go ahead and do that. Again, the idea is the same. If I have a radical in the denominator, I look only at the polynomial inside of the radical, and then I factor the largest power out. Every time that you have a radical, you're going to do that. You're going to take the largest power inside and you're going to factor it out. So in this case, we're going to have the limit as x approaches positive or negative infinity, 2x plus 5, nothing is going to change there, divided by the square root of x squared, 1 plus 7 over x squared. So that's what we get. Now we're going to use the properties of radicals, where we can take the radical of a product. If you remember, let me do it here again. The square root of a times b is equal to the square root of a times the square root of b. I'm going to do that with the denominator. So that's going to give me here the square root of x squared times the square root of 1 plus 7 over x squared. So this is now a step where I want to say something about the square root of x squared. I'm hoping that you remember from grade 11 mathematics is that the square root of x squared, it doesn't just equal to x. It's actually equal to the absolute value of x. You need to remember that whenever you have the nth root of x to the n, there are two possibilities here. If n is even, the nth root of x to the n is going to be equal to the absolute value of x. And if n is odd, then the nth root of x to the n is just simply equal to x. And this is something that I need to be able to assume that you remember and that you feel comfortable with. We don't have time to be reteaching pre-calculus concepts. We really don't. This is one of the reasons why we're even starting right now in the summer studying chapter 2. So if you are in doubt of this, then you're going to come and work with me during tutorial time and we will definitely go over that. Or you can just search this result on the web, look at some videos, and try to refresh your memory about radicals. So in this case, we're going to do the following. We're going to go ahead now and continue by writing the limit as x approaches positive or negative infinity, 2x plus 5 on top, and then in the bottom I am going to write absolute value of x times the square root of 1 plus 7 over x squared. I cannot just do what I did in the previous example in part A. If you remember, in the previous example, I came and I changed the radical to exponent. But here, if I do that, I am going to end up getting exactly x to the 2 over 2, which is x. And we know that this is not always x. Since the index is even, since I have the square root of x squared, then I know that by this approach, by definition, in a sense, this is going to be equal to simply positive x or negative x, right? This is exactly the definition of an absolute value of x. So there are two possible answers depending on whether x is positive or x is negative. So it is important, it is essential that I write absolute value of x right here. And as a result, we will now split this into two separate cases. Case number one will be when x approaches positive infinity and when x approaches negative infinity. So let's do that even in a different color here. So the limit as x approaches positive infinity of 2x plus 5 over, and because x is approaching positive infinity, then the absolute value of x will just be x times the square root of 1 plus 7 over x squared. And then the other case will be the limit as x approaches negative infinity of 2x plus 5 divided by negative x times the square root of 1 plus 7 over x squared. Now, why negative x? Notice over here, negative x because x is approaching negative infinity. So here I need you to remember another, actually the formal definition of an absolute value. So here as a reminder, the absolute value of x is equal to x if x is greater or equal to 0. So as long as x is positive or 0, the absolute value of x will just become x. The absolute value signs disappear. And then the absolute value of x is equal to negative x if x is less than 0. So whenever x is negative, the absolute value of x is equal to negative x. So negative x will be positive because x is negative. This is exactly why I came and I replaced this absolute value of x here with negative x, because now this is the limit at negative infinity. X is approaching negative infinity. So by definition, the absolute value of x will have to be equal to negative x. And again, this separation of positive and negative infinity happened because of the absolute value of x. See, by having absolute value of x, we practically can't continue. We needed to get rid of it. And we got rid of it by applying our definition of absolute values. We had to consider two cases, when x is positive and when x is negative. This is equivalent to two cases here, when x approaches positive infinity and when x approaches negative infinity. By separating the cases, we get rid of the absolute values, and now, yes, we have a little bit of more work, but we can continue with the division process as before. Videos. All right, so let's continue with the analysis. If you notice, I have just copied the original question and I jumped all the way to the second to last step, and then the very last step over here. Now I have to evaluate or to examine each limit at in one direction only, at positive infinity and at negative infinity. So continuing with that analysis, we are going to have that this is equal to the limit as x approaches positive infinity. And here we're going to do exactly as we did in part A. We will take every single term and we're going to divide by x, this factor over here that came from the radical. So then we're going to have 2x over x plus 5 over x. All this divided by x times the square root of 1 plus 7 over x squared divided by x. Now we can cancel the x's. We can cancel this x over here. And we are going to have also applying the limit to the numerator and denominator, we will have the limit as x approaches positive infinity of 2 plus 5 divided by x. All this divided by the limit as x approaches positive infinity of the square root of 1 plus 7 over x squared. When we now apply the limit to 2 and the limit to 5 over x, we are going to get there 2 plus 0 in the numerator. In the denominator, remember that you can take the limit and you can apply it to the inside. So whenever we do that, we are going to get 1 plus 0. That means that we're going to get 2 over 1, and that's going to give us a value of 2 for the limit at positive infinity. In this case, we will practically do exactly the same thing. We're going to go ahead and divide every single term by, you can divide by x or by negative x. It really doesn't matter. So we're going to have 2x over negative x plus 5 over negative x. And I'm going to skip already one step. I am sure that you will be okay if I just skip the step where I write this over negative x. If I divide the denominator by negative x, you know that you will just get the square root of 1 plus 7 over x squared. And you are also allowed to skip this step whenever you're doing the homework exercises. So applying the limit to the numerator, we're going to have the limit as x approaches negative infinity of negative 2 minus 5 divided by x. All this will be divided by the limit as x approaches negative infinity of the square root of 1 plus 7 over x squared. And now when we apply the limit to the first term, the second term, when we apply the limit inside of the radical to the first term into the second term, we are going to get negative 2 minus 0 divided by 1 plus 0. And that is going to give us negative 2 as the value of the limit. So what we notice is that the limit at positive infinity ended up being positive 2. And the limit at negative infinity ended up being negative 2. Even though there was a bit of more work, I'm hoping that you noticed that the process was very, very similar to the process in part A. Here we have part C. We have a limit in both directions at positive and negative infinity of ln of 2x plus 5 minus ln of the square root of x squared plus 7. I wanted to give you something a little bit more exotic involving logarithms because you're going to find that on the homework assignment and on the AP exam, they can throw anything at you. So let's do something like this. The first thing that we're going to do is to use properties of logarithms to condense this difference into one single ratio. So using properties of logarithms, we're going to have that this is equal to the limit as x approaches positive or negative infinity of the natural logarithm of 2x plus 5 divided by the square root of x squared plus 7. So whenever you see natural logarithms and you recognize that you can condense a difference or a sum of logarithms, please know that you can do that. You can apply your properties of logarithms, the properties that you learned in pre-calculus last year. All of those properties are perfectly valid when working with limits as well. So in this case, by condensing this difference into this fraction here, I want you to notice that the expression that we obtain now here inside, this rational expression, is the same expression that we were working with in part B just a few minutes ago. So when working out the limit, I am not going to have to repeat all the work that I did in part B. I already have that work. I will take advantage of that work. So here, the limit will be applied to the inside. And that's because this function is a composite function. It is a composition where the inner function is the non-rational function and the outer function is the logarithmic function. And you know that by properties of limits, we do have a property that tackles composition. The property says that if this limit over here exists, then the entire analysis can begin by working the limit from the inside into the outside. So let me go ahead and begin that analysis. So in this case, we're going to have the ln of the limit as x approaches positive or negative infinity of 2x plus 5 divided by the square root of x squared plus 7. Now again, I already did this limit. We did all that work in the previous example. So I will only be using the final result of that example. I don't have to go ahead and work this limit out. If that was not the case, then yeah, you're going to have to do exactly what we did in part B for the inside only. So yours is quite a bit of work, but it's perfectly doable. So in this case, these are the two scenarios, number 1 and number 2. The limit as x approaches positive infinity versus the limit as x approaches negative infinity. We're going to have to consider those two cases separately because that's exactly what happened with the inside in part B. We had two separate answers. So for two separate answers, two different cases. So continuing, this will be equal to the ln of the limit as x approaches positive infinity of 2x plus 5 over the square root of x squared plus 7. And over here, we are going to have the ln of, again, 2x plus 5 over the square root of x squared plus 7. Then, in the first case, if you remember, the limit at positive infinity of the function ended up being positive 2. So then, all this over here can be replaced with positive 2. That means that the value of this limit is just ln 2. But then, when we go to this case over here, then we have an undefined situation because the limit inside ended up being negative 2. And we know that the ln of negative 2 is undefined. So this limit actually doesn't exist. It doesn't exist because we know that the domain of a logarithm only consists of positive x values. So as soon as we put a negative 2 over here, even though the limit of the inside beautifully exists is equal to negative 2, the natural logarithm of negative 2 makes no sense, is completely undefined. So then at the end, we get an undefined value for the actual limit at negative infinity. Let's tackle example D. This is another limit at positive infinity of another non-rational function. The only thing is that the radical in this case is in the numerator. And I'm afraid that if I don't do an example where the radical is in the numerator, you may feel a little bit insecure at first. And I don't want you to feel like that. I want you to notice how the steps are identical to the steps that we followed in parts A and B of example 1. So the first thing that I'll do is to factor the largest power from the numerator. And the largest power is x to the third. Let's factor that out. So that will be the square root of x to the third times 1 plus 20x over x to the third. Then this will be divided by 10x minus 2. Nothing changes there. Now using properties of radicals, we're going to go ahead and separate. We're going to separate this radical right here. So we're going to have the square root of x to the third, that's going to come out, times the square root of 1 plus 20 over x squared, because I am also simplifying this last term right there. That's going to be equal or divided by 10x minus 2. So just quickly observing this red square root of x cubed here, I want you to notice that as x approaches positive infinity, the radical is perfectly defined, because if x is positive, x to the third is positive, the square root of a positive number is always defined. So in my next step, I'm going to take the radical and turn it into an exponent. That means that we're going to have the limit as x approaches infinity of x to the 3 over 2 times the square root of 1 plus 20 divided by x squared over 10x minus 2. And now we are going to go to the denominator. We're going to take the largest power and we are going to divide the numerator and the entire denominator by the largest power. The largest power happens to be x. So we are going to have the limit as x approaches infinity of x to the 3 over 2 times the square root of 1 plus 20 over x squared divided by x. All this divided by 10x over x minus 2 over x. So again, the numerator, all of it, was divided by x, and the entire denominator was also divided by x. So now, simplifying. Let me continue right here. So simplifying this, we're going to have the limit as x approaches infinity. And now what I need to do is to simplify this radical right here. This is going to give me x times the square root of 1 plus 20 over x squared. That will be divided by 10 minus 2 over x. In my next step, I'm going to go ahead and apply the limit to the numerator and then the limit to the denominator. So this will be x times the square root of 1 plus 20 over x squared. All this divided by the limit as x approaches infinity of 10 minus 2 divided by x. Now, when we apply this limit to the product that we have here, we know that because of this x, this limit will remain infinity. This one is going to go to 1, this term is going to go to 0. So practically then in the numerator, what I have is infinity times, if you want to informally write this here, 1 plus 0. And again, informally, because remember, even though this seems like multiplying by infinity, infinity is not a number, it's just a concept. What we're saying is that infinity times anything else that is finite will remain being infinity. And then this will be divided by 10 minus 0. So in a sense, what we have is something like infinity over 10, which is going to give us infinity as a final result. And just to remind you again that having infinity over 10 is not an indeterminate situation. Infinity over 10 is considered to be infinity. And also remember that getting an answer of infinity doesn't mean that the limit exists. The limit doesn't exist. The infinity is just telling us that as x approaches positive infinity, the y values of this expression, they go off to positive infinity as well. It's just describing, infinity is just describing what is happening to the y values as x approaches positive infinity. As x approaches positive infinity, the y values are growing, are getting larger and larger and larger as well. In example 2, they're asking us to find horizontal asymptote or asymptotes if they exist of the following function. This is the function. This is a non-rational function. We need to remember the concepts that we developed in the introductory video of this section, the very first video. There we said, if you remember, we said there that if we take the limit as x approaches positive or negative infinity of a function f of x, and we happen to get L, a finite real number, as the value of the limit, then that meant that the line y equals x, or excuse me, y equals L is a horizontal asymptote. So that's exactly what I have to do here. I'm going to have to consider the limit at positive infinity and the limit at negative infinity, and I will try to observe what I get. If I get a fixed number L as the value of the limit, then I found horizontal asymptotes. But if I get negative infinity or positive infinity, then that means that there will be no horizontal asymptote. Now, beginning the algebra, that's good news because it's going to be pretty much identical to the process that we followed in the previous examples. I am going to focus on the denominator because this is where I have pretty much a radical. Having exponent of 1/6 is equivalent to having the 6th root of that expression, of that quadratic. So my radical is in the denominator. So the first thing that I'll do is I will look at the inside of the radical and I'm going to factor the largest power out. So let's do that. I'm going to factor the largest power, and I'm going to have to consider two cases here. The case at positive infinity and the case at negative infinity, as I said a few seconds ago. So let's do case number 1. This will be the limit as t approaches positive infinity of t to the 1 over 3 divided by 64 t squared plus 9 to the 1 over 6. And what we're going to do is, as I said a few minutes ago, we're going to look at our denominator. This is where the radical is located. Remember, having exponent of 1/6 is the same thing as having the 6th root. We're going to take the largest power, in this case t squared, and we're going to factor t squared out. Similar process as the previous examples. We're going to have the limit as t approaches positive infinity, t to the 1 over 3, divided by t squared, 64, plus 9 over t squared to the 1 over 6. Now I have this factor, t squared, and this other factor, 64 plus 9 over t squared. I will apply the exponent to each factor. In that case, we're going to have the limit as t approaches positive infinity, t to the 1 over 3 divided by t squared to the 1/6 times 64 plus 9 over t squared to the 1 over 6. And this is a case now, this is a particular point in this algebraic analysis that we're going to have to be a little bit careful. Look at this expression right here, t squared to the 1 over 6. I don't want you to rush there and say, all right, t squared to the 1 over 6, this is equal to t to the 1/3. This is partly true, but you need to always be cautious when dealing with exponents, when dealing with radicals. Look at this. T squared to the 1 over 6 is always positive. Because t is being squared, t could be positive, t could be negative. But because of the squaring process, if t is negative, we're going to end up getting a positive result. So this expression right here, t squared to the 1 over 6, is always going to be positive. This is always equal to a positive number. However, if you now look at t to the 1/3, t to the 1/3 can be positive and it can be negative. If t is positive, t to the 1/3 is positive. It's like having cube root of t is positive. If t is negative, the cube root of a negative number is negative. So how can a number on the left that is always positive be equal to a number on the right that could be negative? We have to be super careful here. And because we are considering two cases, when t goes to positive infinity, when t goes to negative infinity, this equality, saying that this is equal to t to the 1/3, it's a little bit inaccurate unless we put absolute values around t to the 1/3. If we enclose t to the 1/3 with absolute values, then yes, this is always true. So in this case, the proper way, if you want to be super, super proper, you're going to go ahead and write the limit as t approaches positive infinity of t to the 1/3 divided by the absolute value of t to the 1/3 times 64 plus 9 over t squared to the 1/6. So this is a crucial step, something that you need to be super careful when dealing with exponents, hence with radicals, particularly rational exponents. Now, do we really need to keep the absolute value in the case where we're considering limit at positive infinity? Hopefully the answer in your mind is no. Because we are considering the case of t approaching positive infinity, t is positive, so t to the 1/3 will be positive. So again, t to the 1/3 is positive. That means that we don't need the absolute values in there. So I will just write the limit as t approaches positive infinity of t to the 1/3, all this divided by t to the 1/3 times 64 plus 9 over t squared to the 1 over 6. So again, here the absolute values were redundant because we are considering the limit at positive infinity. However, when we go back, when we actually do case number 2, that will be the opposite limit, the limit as t approaches negative infinity. We are going to remove the absolute value, but we're going to place a negative in place of the absolute value. All right, so that will be though in case number 2. Let's continue this case. Now that I got rid of the absolute values and I have this, we're going to do the same division process. We're going to look at the denominator. We're going to look at this factor that is completely by itself that came from the inside. And we are going to divide numerator and denominator by t to the 1/3, just as we did before. So this will be the limit as t approaches positive infinity, t to the 1/3 divided by t to the 1/3 divided by t to the 1/3 times 64 plus 9 over t squared to the 1/6 divided by t to the 1/3. And then we notice that this will cancel out, this will cancel out, and we are going to end up getting the limit as t approaches positive infinity of 1 divided by 64 plus 9 over t squared, all this to the 1/6. Now we will apply the limit to the numerator, the limit to the denominator. I'm going to skip that step of rewriting everything with the limit on top and the limit below just to save a little bit of time. And we will continue by just taking the limits. So in this case, the limit as t goes to infinity of the numerator of 1, that will just be equal to 1 divided by the limit as t goes to positive infinity of the inside, so of 64, that will give us 64 plus the limit as t goes to infinity of 9 over t squared, that is going to be 0. This will be all raised to the exponent 1/6. Continuing here, this will be equal to 1 over 64 to the 1/6, which is going to be equal to 1/2. And this is the beautiful part. The limit at positive infinity is equal to a positive fixed real number. That means that the line y equals 1/2 is a horizontal asymptote. Let's write that. Therefore, y equals 1/2 is a horizontal asymptote as t approaches positive infinity. So now we're going to go ahead and do case 2, pretty much repeating many of these steps. Pretty much the entire setup will be identical, with the exception that now we're going to be considering the limit as t approaches negative infinity. Here is now case number 2. If you notice, we are dealing with the same function. The only difference is in the limits. I have updated the limit to the limit as t approaches negative infinity as opposed to positive infinity. However, all of these preliminary steps are identical, so I just copied and pasted. And here I am back to the absolute value. And as I said before, in my next step, I will have to eliminate the absolute value, and I'm going to do that by placing a negative because now t is approaching negative infinity. So t to the 1/3 has to end up being positive, and the only way that I can make that positive is by placing absolute values. And I know that t to the 1/3 has to be positive, if you remember, because of this green selection right here. Do you see it right here above? T squared to the 1/6. Prior to simplification, t squared to the 1/6 has to be positive. I'm going to put a plus over here. So when I simplify the exponents to 1/3, I have to make sure that everything is still identical. A positive number still equals to a positive number right here. So the absolute values are making sure that I get a positive result. And if I'm going to eliminate the absolute values, I have to place a negative in front of t to the 1/3 so that everything remains being positive. That will be my next step. I'm going to have the limit as t approaches negative infinity, t to the 1/3 divided by negative t to the 1/3 times 64 plus 9 over t squared to the 1/6. Now that I do that, I will take the numerator and denominator and I will divide by t to the 1/3. So that is going to give us here the limit as t approaches negative infinity, t to the 1/3 divided by t to the 1/3 over negative t to the 1/3, 64 plus 9 over t squared to the 1/6 divided by t to the 1/3. The t's to the 1/3 will cancel out and we are going to have the limit as t approaches negative infinity of 1 divided by negative brackets 64 plus 9 over t squared to the 1/6. Now I will skip the step where I write the limit on top and the limit below. Hopefully by now we're getting the hang of these things. And the limit of the numerator is going to be equal to 1. The limit of the denominator will be equal to 64 plus 0 to the 1/6. So all this will be equal to 1 over negative 64 to the 1/6, which is going to be equal to negative 1/2. And negative 1/2 is another fixed real number. So then that means that we have another horizontal asymptote. So therefore, y equals negative 1/2 is a horizontal asymptote of f of t when t approaches negative infinity. So we have two horizontal asymptotes essentially. This is what is happening here. I have a horizontal asymptote at y equals 1/2, and this graph will have a horizontal asymptote at y equals negative 1/2. How lovely.